let's continue. Okay? So, just a theta dot a theta is rho, this is 1, and this is rho squared. Then, the dot product by definition, okay, is magnitude, magnitude, and cosine of 0. Okay? Then, the magnitude square is equal to rho squared. Then I conclude that the magnitude of this base vector is just rho. Okay? A rho dot a rho will be 1. Done with this clearly, you can see that. You see? The magnitude of this base vector. Now, you see how interesting. If you multiply dot product, a theta, a rho, this will be 0. Okay? Just easy. Okay? Just multiply will be 0. But a theta is scalar, a theta will not be 0. So this will be rho squared. Okay? That we saw that. Now, let's emphasize the floor. Okay? Don't forget this. This behaves like floor. This is x and y, or x1, x2. You see the unit vectors are e1, e2. You see? Now, look the sign. Okay? Y, first of all, consider theta belongs to the first quadrant. Okay? So, theta will be an angle in radian. Okay? Like pi over 3, pi over 6, pi over 4. Okay? Doesn't matter. Belongs to the first quadrant. So, then you see here, you see that cosine is positive, sine is positive, sine is positive, but this here will be minus. So that's easy. That's why, look at that, how easy. This over here, this blue one, is the x1 direction. This is here, see? Don't forget that. This is x1. This is x2. See? The rectangular coordinate. Theta is the angle between x1 and this vector here, a rho. Okay? A rho. Now, we came up with this relation here, a rho is equal e rho. You see the symbols here on the top. So, there's a unit vector. But a theta is not unit because a theta is rho e theta. Why the direction is this way? Okay? It's easy to see here because if you project this rho f theta on the x-axis, you see here the arrow, this will be negative. But the projection in y will be positive for theta. Now, belongs to the first quadrant. But a rho, okay, the arrow points this way because if you project a rho over x1, this will be cosine, will be positive. And also if project a1 in the y direction or x2 direction, always will be positive. That's why a rho points in this direction, but a theta points in this direction. Okay, that's as shown in this figure here. Now, I can okay, divide a theta divided by rho, because rho is a scalar quantity. In general, no, it's always different from 0. It's the radius of the cylinder. So, if I divide a theta by rho, I have a unit vector here, you see? So I can say that E sub rho, E sub theta, E sub z, they are now orthonormal base vector in cylindrical coordinates. You see? You have always to pay attention that the E rho is naturally, okay? You don't have to do anything, just to to play the derivative, this is equal a rho, because you prove that a rho dot a rho is 1. But a sub theta, if you dot a sub theta dot a sub theta, this will not be 1. So, okay, so I will emphasize here just for you to understand. A rho, a theta, a z are the base vectors, or this system, okay, is not orthonormal, but it is orthogonal. To move to the orthonormal, I have to divide this vector here, divide by rho. Then I can write right here. This is, okay. Here's a dot product between a rho, a theta will be 1, a sub rho, a z is 0, a rho is 1, a theta dot a theta will be 1, and a z dot a z will be 1. This is orthonormal base vector. Okay, the point, okay, I'm doing here, and I emphasize, is this: the base vectors, they are obtained by partial derivative of position vector. Keep this in mind, see, because you're going to use this result, okay, just when you move to any curvilinear coordinates. See, always the base vector not necessarily will be orthogonal, not necessarily will be orthonormal. I can have a base vector which each element of this base vector, the dot product, is not necessarily orthogonal. For instance, in general, A1 dot A2 is not necessarily 0, because A1 and A2 are not necessarily orthogonal. See? So these are particular case. See? This, look at here, particular case of curvilinear coordinates. Okay, next, just for you to become familiar, okay, I'll talk about spherical coordinates. Okay? But remember, particular case, cylindrical and spherical. Okay? Because in general relativity, you use some model with employing spherical coordinates. Okay? Schwarzschild model. The other examples in the general relativity, we use in this case spherical coordinates. Spherical coordinates is important for our objective, which is a long way to go just to reach the Einstein field equations.